the topic of my talk today will be trying to figure out how to, well, understand the thermalization process, not just qualitatively, but even quantitatively, and how to sort of bridge the gap between some microscopic description of the dynamic of anybody system and the effective long wavelengths, long time description that you have, which is described by hydrodynamics in many cases. So we generically expect that in a thermalizing system, if you go to long enough times, many features of the dynamics will be described by some sort of hydrodynamic theory, and I will talk a little bit about that in a second. But this is some sort of effective field theory which has some parameters going into it, and there is a gap to be bridged between this effective description and the original microscopic description at the level of something like a many-body Hamiltonian that you start with. So what I will talk about is a method that we came up with for trying to bridge this gap and start with some microscopic Hamiltonian and figure out even quantitatively what is the hydrodynamic behavior. And it's described in this preprint that we put on the archive a few months ago. So yeah, I will first give a little bit of an introduction of what I mean by hydrodynamic transport. And then I'll describe the method that we came up with, and then finally show you some results and try to convince you that it actually works quite well and gives you reliable results. So the basic idea is that transport is one of the very fundamental ways in which we can probe how a many-body system behaves. So if you have some conserved quantities, some extensive conserved quantities described by their local densities, which obey a local continuity equation, and these can be things like energy, particle number, spin in some systems, and so on, then these are very special in their dynamical behavior in the sense that they lead to very slow relaxation in a way. Because for things that are not conserved, if you perturb the system a little bit, it can just locally relax back to equilibrium. And this can happen very quickly. But if you have a conserved quantity and you create some excitation, the only way for this excitation to relax back to equilibrium is if you transport the excess conserved quantity across the system. And if your initial perturbation has some very long wavelength, then this will take a very long time. So in the limit of large wavelengths, the relaxation time diverges. And this means that these are very, very slow modes, and these will be the most relevant for describing dynamics on the longest time scales. And there can be some other ones in other situations. For example, if you have Goldstone modes, they also give you slow modes, or if you're close to a phase transition and so on. But today I will be mostly interested in the high temperature regime, where really these conserved quantities are the only relevant slow modes. And these are also very important for understanding the transport behavior. And within linear response theory, these are encoded in calculating equilibrium dynamical correlations. So these are unequal time correlators of the conserved densities, but they're evaluated in equilibrium. And if you knew all of these, you can use this to calculate all the important transport properties at the level of linear response are encoded in these. So what can we say about their behavior? And as I was saying before, we expect that at long times in a generic system, there will be some emergent hydrodynamic description. So we're interested in a regime where the interactions are strong and the temperature is high enough that you don't really have any long-lived quasi-particles. So the sort of quasi-particle Boltzmann description breaks down. And the only thing you are really left with is hydrodynamics, in the sense that if your system is generic enough, you expect it to thermalize. But if your initial state is inhomogeneous, what's going to happen is that it's going to locally thermalize in each region. So you can take some region of the system, which is large compared to the microscopic scales, but small compared to the whole system. And after some initial short relaxation process, this will be well described by a thermal equilibrium. But in a thermal equilibrium, where things like the temperature or the chemical potential can depend on where you are in space. So this is what is called a local equilibrium state. And in this local equilibrium state, then the only variables that remain are really the constant quantities that label these Gibbs-like states locally. And the only remaining dynamics is, or at least as far as transport is concerned, is how the temperature profiles or chemical potential profiles smoothen out in time as you go further. And using this assumption of local equilibrium, you can sort of expand the equations of motion. You get closed equations of motion for your constant quantities. And if you expand this to lowest order, what you end up is some sort of diffusion equation for the constant quantities. And here we are assuming that we are in a system where there is no momentum conservation. So for example, we are dealing with lattice systems, which break translation symmetry. Otherwise, you would also get you would get a more complicated type of hydrodynamics described by Navier-Stokes equation. And what's interesting here, that I like to point out, is that this diffusion equation is a dissipative transport equation, but here this dissipation arises in an entirely closed system. So this doesn't come from interaction with some environment, some phonons or impurities. This is entirely dissipation arising from the internal dynamics of the many-body system. And this is kind of a defining feature of what I would call a hydrodynamic regime.
Tibor, can I ask a question?
Yeah, sure.
So you said that because we're living on a lattice, we can ignore about momentum conservation, but you would expect, say, low momentum to still be, be meaningful on a lattice, right?
You have lattice momentum, but that doesn't really enter in this hydrodynamic description.
I see.
So because it's periodically defined, so it doesn't really make, like, normally for momentum, you have some continuity equation that you have more momentum in one region and less momentum in the other, and then you have flow of momentum. But it doesn't really make sense when it's periodically defined. You can't really say which one is more and which one is less.
I see. So in practice, you can just ignore this quantum number?
As far as the hydrodynamics is concerned, yes. So you don't really expect to get a difference between something with discrete translation invariance versus something where you even break that.
I see. Thank you.
Okay. So you have these different scales. You have some microscopic scale which is described by your many-body Hamiltonian, and where you sort of think about individual particles. And then you have a much larger scale, this hydrodynamic scale, where you coarse grain enough that you have a local equilibrium everywhere, and you can really just focus on a few variables, the densities of constant quantities everywhere. And the question is how to bridge this gap between these two scales. If you have something like a weakly interacting gas, then you can use a Boltzmann equation, which kind of provides a way of getting from one description to the other. But we are interested in systems where interactions are strong and you cannot really apply a Boltzmann equation. So the question is how to bridge this gap, and how to do this even quantitatively, that you can actually predict not just the qualitative features of the hydrodynamic description, but even the quantitative, the numbers that characterize it. And just want to point out that this hydrodynamic regime is quite relevant for many different experimental settings. So in some sense, cold atom experiments are the most relevant, where you really have these closed quantum systems that I had in mind in my introduction. But you can also have some quantum magnets where spin transport is also at high temperatures well described by some hydrodynamic description or some diffusive behavior. And there are also cases where you can think of electron transport in graphene or some other materials, where you can get to a regime which is really described by hydrodynamics rather than the usual sort of Boltzmann Fermi liquid description. And finally, while I was talking mostly about transport here, there is a slightly different angle that you can take here, which is the question of thermalization. So you can imagine having your closed quantum system and starting in some pure initial state, evolving it in time, and looking at its evolution as a function of time. And here again, you would expect that if you go to long enough times and you sort of look at coarse-grained large distance behavior of, let's say, your constant quantities, or even many other things, so some local observables, these are mostly dominated by these hydrodynamic descriptions. So in some sense, the dynamics at long times looks fairly simple. But this is in contradiction with the fact that the state, as it's evolving, becomes increasingly complex. So for example, if I looked at the entanglement of this state, that as it's evolving, it's growing linearly in time. So it's becoming a really entangled, really complex state. So this leads to something that you can call the information paradox of thermalization, that the complexity of some classical description of your time evolving state, it increases very sharply initially, exponentially basically, at least if you think of something like a tensor network representation. But then at long times, you expect to have, again, some relatively simple description, at least approximately, that describes this hydrodynamic behavior. So the question is sort of how to bridge this gap between these two.
Tibor, can I ask another question?
Yeah.
So yeah, that sounds very interesting, and I'm trying to understand how particular is it to a quantum system. If we imagine starting with some simple classical system, and you might also think, right, it costs a lot of information to keep track of all the particles, but then eventually some simple stat-mech kind of description.
Yeah, I think that's true. I think there is some classical analog of this in terms of just because of classical chaos, to really follow the dynamics becomes, of course, extremely complicated in practice. But then if you are looking at some particular variables, you should again enter a regime at long times where you can just use some hydrodynamic approximation. But yeah, I think there is an analogous problem even at the classical level, but I haven't thought too much about it.
But classically, you don't need exponential number of bits, right?
Well, don't you need, like, doesn't sort of chaos tell you that in some sense, if you wanted to do this exactly or to a very good precision, it would be exponential? Sort of the Kolmogorov-Sinai entropy would take the role of the entanglement entropy.
Yeah, perhaps. Thanks.
I'm not 100% sure, but that's my intuition.
Yeah, Tibor. So what is this time scale, tau th, you have in mind?
Yeah, so here I'm being fairly sloppy in defining that. I would say that there is some local thermalization time it takes before you can apply this hydrodynamic approximation. So if you have some coarse graining in mind, some fluid cells which are large enough that you can imagine a fluid cell sort of thermalizing by its own dynamics, then you can ask how long it takes for that thermalization to happen. And so, yeah.
Right, yeah, so typically say at strong coupling, if you look at the local thermalization time, so that would be just order beta. So here you have in mind just order beta, or you mean some higher, larger time scale?
No, well, I think at high temperatures, I will mostly be talking about infinite temperature later on. It would be an order 1 time scale. And yeah, I think order beta is probably correct. But so I will maybe slightly later on, I can give a slightly more quantitative definition of what I mean by this. When I can show you some plots.
Okay.
Okay, so there's this question of how to try to bridge this information gap and try to get some description of the time evolution, which, even if it doesn't capture everything, because that's too much to ask for, it captures the physically relevant features on all time scales. It can capture things happening at short times, but it can go over this region and enter this hydrodynamic regime and correctly capture the relaxation on those time scales. And the standard things you would do, like tensor networks or just some exact Krylov dynamics on small systems, those are all limited by either by entanglement or by the system size. They can give you some short time behavior, but it's a question whether that's long enough to really go beyond this thermalization time, and in many cases it isn't. So we'd like to do something better. And there are various proposals which I've listed here, but and these are all quite interesting, but in most cases they have not really yet demonstrated the ability to really get this hydrodynamic behavior correctly. And even in cases where they do get some hydrodynamic behavior, for example, these papers by Marko Žnidarić are very interesting. He takes a quite different approach. But the problem with these is that it's somewhat uncontrolled. So you get some result for things like diffusion constants, but it's hard to tell how reliable that result is. So there are sort of things that you have to adjust by hand to some extent. So what I will try to convince you is that the method we came up with, not only can it reach the hydrodynamic regime, but we have some control. It is quite well controlled. We have some parameters that we can tune to check that indeed the result we get is actually the correct one. So this is what I will turn to now. So our goal, what we want to do is, again, with a linear response, calculate these dynamical correlations between conserved densities at different positions and times. And for this talk, I will focus on infinite temperature. So extending it to finite temperature is an interesting thing we want to do in the future, but so far we looked at infinite temperatures. And it will be quite useful to rewrite this correlation as something like a propagation amplitude in the space of operators. So what I can do is take my operator and I can think of it as a state living in a larger dimensional Hilbert space. In a tensor network language, this is very simple. You have a matrix product operator, and then you just combine its two physical legs into a single physical leg so that it looks like a state. But this is just a statement that the operators also form a linear space, so you can also think of them as states if you want. And in this language, a correlator like this becomes the amplitude of going from some initial operator to some final operator. And the time evolution between the two is generated by what is known as the Liouvillean, which is essentially just a generation of time evolution in the space of operators. So what we want to do is take our initial operator, evolve it in time with this Liouvillean, and look at its overlap with the final operator, which is a density on some other site, x. But the problem with this is that if I evolve this operator in time, it also has this exponential growth of complexity. So you could think of the operator entanglement, which is the entanglement of this matrix product operator description. And in the middle, where in the initial location of the operator, this just grows linearly in time. So just like in the case of evolving a state, you have the numerical cost grows exponentially in time, and this limits you to very short times if you wanted to do this exactly. So the key idea that we had is to realize that we don't really want to do this exactly. We don't really need this operator as such. The only thing we really need is the part of the operator that has an overlap with the other conserved densities. So you only really need a small part of this time evolving operator, not all of it. And if you think of the dynamics within this restricted space, as I said before, we expect this to be dissipative. So restricted to this subspace of conserved densities, the dynamics will no longer be unitary. So we can try to modify our dynamics, make it dissipative by hand in a way that kind of captures this dissipation that's inherent in the unitary dynamics as well. So how to do this in practice? We do the following. So first of all, we take some basis in the space of all operators. So let's imagine now that we have a one-dimensional spin chain for simplicity. And then a basis of all possible operators for spin 1/2 chain is given by strings of Pauli matrices. So on each side, I have to specify either the identity or a Pauli matrix X, Y, or Z. And if I take all possible products like this, these form a basis, and any operator can be written as a linear combination of these. And the idea is that the physically relevant observables that we care about depend only on the parts of the operator that contains Pauli strings, which are simple in the sense that they only contain a few operators that are not the identity. So we can classify these Pauli strings according to what we call their length or their complexity of how many different sides they are acting on. And in some sense, the longer a Pauli string, the less important it is for the physical transport behavior we are interested in. So the idea is that we can throw away a lot of the information related to these long Pauli strings while keeping correctly the information related to the short Pauli strings, which are the ones that we really need to correctly capture the transport. And the way to do this is to introduce a super operator, which we call D for being a dissipator. And what it does, it has two parameters, L star and gamma. So L star is a cutoff, which tells us that if we have a Pauli string whose length is shorter than this cutoff, then the dissipation doesn't do anything. So certain operators are just not affected by this dissipation. And this is something we need in order to make sure that by doing this dissipation, we don't disturb the conservation laws that we are interested in. So if you have some conserved quantities, we should make sure that this L star is large enough that the densities of conserved quantities are not affected by the dissipation. And for any Pauli string that is longer than this cutoff, we multiply it by a prefactor, which is exponentially small in its length. It's e to the minus gamma times the length of the Pauli string minus the cutoff. So what this dissipator does, it keeps the short part of the operator and it decreases the weight on all strings which are long. And the longer the string, the stronger it gets dissipated. And what we do is we interchange the unitary evolution with this dissipation. So we evolve the operator unitarily up to some time delta t, and at every delta t, we hit it with this dissipation. So we let it evolve a little bit without, as it would unitarily, and at a certain time, we throw away some of the information contained in these long strings. And then we again let it evolve on its own, and then again, we hit it with the dissipation and throw away some of the information. So the idea is that by doing this, and by making the dissipation weak enough, we can go to a regime which we can still simulate, but at the same time, we correctly capture the hydrodynamic behavior, which is mostly encoded in the behavior, in the part of the operator that's made up of short local operators. So let me stop here for a second for questions, because this is, in some sense, this is the central slide.
Yeah, I had a question here. So the way you've discussed it now, it actually doesn't sound like you're throwing anything away, right? You're just multiplying with a small factor. Like, why does it help in terms of tensor network description? Or are we reducing any bond dimension?
Well, most of this growth of operator entanglement, it comes from the long Pauli strings in the operator. So if you just do the unitary evolution, most of the weight will be on strings which have a size that grows linearly in time, basically the size of the Lieb-Robinson cone. Mm-hmm. And because there are much more operators which are long than there are short, that's sort of the reason why you end up with a linear growth of entanglement. By doing this dissipation, you sort of change the relative weight of long versus short operators. And how should I say this? So, I mean, one way to imagine this or to see that there is a reduction of entanglement, if I made this dissipator really strong, my operator would be entirely made up of a short operator, which is a much smaller space where you cannot grow as much entanglement.
Right. No, I definitely see how it reduces the entanglement of the operator, but I guess I don't see how it reduces, say, the bond dimension. Or is it just because it depends on where you truncate Like this will, it will push more things below the truncation error or something?
Exactly,
I
exactly.
see.
So what happens is that, yes, of course, yes. So if you still wanted to do this exactly, then you wouldn't gain anything. But the point is that if you do this modified evolution, you can approximate it very well with a finite bond dimension.
I see. Okay. And just maybe a quick second question. So the earlier you said you had this tuning parameter. Is that this gamma that if you check that if you make gamma small enough that you know things don't change, or?
It's basically both of these, the gamma and the L star. So what we will do later on is, one thing is that you fix an L star and then you tune this gamma to smaller and smaller values and try to converge to something that's independent of gamma, as you were saying. But having the L star is quite useful in that it gives you a way to cross-check this, to see that if you do this with a different L star, you get the same result. Because otherwise you could get some sort of false convergence where it looks like you're converging to something as you decrease gamma, but maybe it's not like the actual physical result. So by having this additional parameter that you can have several different approximations and compare them, that gives you more confidence that what you get is actually physical.
Thank you.
Can I ask a question?
Of course.
Maybe you said this, but I didn't catch it. Is there a physical picture I should have in mind thinking about why these long strings are penalized?
Yes, that's actually, yeah, let me go to the next slide. So I think the most intuitive physical way for me to think about this as something like a path integral in the space of operators. So you start with a simple local operator, and you want to end up in a simple local operator because, again, you are looking at an amplitude from a simple operator to a simple operator. And you can imagine different paths. You can imagine paths which remain simple, and by simple I mean local at all times, or you can imagine paths which go out to very complicated objects and come back. So the physical intuition is that paths which go out to very complicated, extremely non-local operators are unlikely to come back. And the contribution coming from these paths where you go very far out and come back is actually decreases with how far you go out. And
I see. So they won't contribute very much to this correlation function.
Exactly.
Okay.
And then basically what this dissipator does, it just gets rid of certain contributions in this path integral, and it gets rid of those contributions which we expect to be small anyway.
So you're not saying that somehow long operators are dissipated more strongly? Or maybe you are saying that since they don't contribute to the correlation function.
Well, I think the way to think about this is more that you could say you split the space of all operators into the ones you are interested in and everything else, so like the conserved densities and everything else. And then so there's a physical dissipation, which is the dissipation from conserved densities to other operators. And there's this artificial dissipation, which we put in by hand, which are not quite the same. But the point is, it's more that once you are dissipated, once you go out to some very complex objects, by the unitary, well, they are more strongly dissipated in the sense that by the unitary dynamics, they are even more likely to become more complex at longer times, and they are less likely to become less complex and go back to this subspace you're interested in.
Okay, thanks.
And this is actually, so there are similar ideas which have been around for a long time called in something called the memory matrix formalism, which is sort of a standard way of trying to describe this hydrodynamic transport, where our parameters basically play the role of the memory time, which is, again, the question of if you leave this subspace of slow operators, how long that, like, assuming you don't return within a certain time, then you're likely never to return anymore. But the point is that in our case, this is turned into a numerical algorithm that you can just apply to arbitrary systems. Well, in our case, arbitrary 1D systems. But in the memory matrix formalism, it's more of it's formally very nice, but it's hard to do an actual calculation in a concrete model with it. Okay, so unless there are any more questions, let me move on. So this is the physical idea that you do this dissipation and you throw out these long Pauli strings, but how to do this in practice. And it turns out that you can do this very nicely and easily in a tensor network language. So you imagine a one-dimensional chain. Again, you turn your operators into states. And then the unitary part of the evolution you can do just by using one of the existing methods for time evolving matrix product state. So for example, for a nearest neighbor Hamiltonian, you can just use TBD, but you could use some other more complicated method if you had a longer range Hamiltonian. And the dissipation part is something that we can represent as a matrix product operator. So it's a super operator acting on this space. And it has a simple MPO representation. In particular, it has a bond dimension, which is equal to L star plus 1. So for those of you who are interested in the details, basically the local tensors in this MPO, they are diagonal in the physical indices because they don't change the operators. And in the bond indices, what you have is that whenever you see a non-trivial operator, you have something like a clock that sort of goes up by 1 whenever you see a non-trivial operator until you hit the cutoff L star, and after that you always just multiply by e to the minus gamma. So it has a fairly simple structure. Okay, so we can actually do this evolution numerically quite efficiently and see what happens. And as a testing case, we looked at the non-integrable Ising chain. So this is an Ising Hamiltonian, which has both transfers and longitudinal field to break integrability. And this is something that people look at a lot in terms of thermalization. And the key point is that, as mentioned before, by doing this dissipation repeatedly every delta t time, what happens is that we limit the growth of entanglement. So if you look at the entanglement of the operator, without dissipation, it would want to grow linearly. But once it realizes that there is a dissipation, then it leads to a peak and then a decrease. And well, the weaker the dissipation, the larger this peak. But as long as the dissipation is strong enough in some sense, we will be able to capture this modified dynamics exactly by using a finite bond dimension. So basically, given a certain limitation of the bond dimensions we can use, will give us a limitation of how weak we can make the dissipation, that's such that we can still capture the dynamics. And what I show here, this is checking how well the conservation law is satisfied. So looking at the sum of these correlations, they should be equal to 1 in the proper normalization due to the conservation law. And if the bond dimension is too small, then there are truncation errors, and the truncation errors, they screw up the conservation law and make it not conserved anymore. But by applying the dissipation, we actually get to a regime where at a certain point, the conservation law becomes fulfilled at basically arbitrarily long times, because you only need a finite bond dimension to capture the evolution up to as long as you want. So thinking back of what I mentioned in the introduction, this is basically this sort of information paradox gap that we have, that there is a peak that we have to go through here, but by applying the dissipation, we sort of cut off the size of this peak, and we get something that we can actually follow through this whole evolution up to the long time limit. Okay, so this is the method that we came up with. And then in the last part, in the last few minutes, I will show just a few examples of how this works in practice and what results we got from this. So first of all, we would like to check that indeed the the transport we get is actually diffusive, and that we have some chance of correctly capturing the diffusion constant. So first of all, we can look at this correlation, this dynamical correlation. And if the dynamics is diffusive, then at long times, this should be described by a Gaussian whose width increases as square root of time. So first of all, we indeed see that while at short times there is some non-universal behavior, as we go to long enough times, indeed, we see a nice Gaussian shape emerging, which is already nice. And then we can look at the variance of this Gaussian distribution, which is called the mean square displacement. So it's just the variance associated to this curve. And what we see is that if we did this time evolution exactly, so these first 4 curves are just exact numerics on small chains, you see that the mean square displacement starts to grow, but at a certain time, the finite size effects kick in and it just saturates to a constant. And using our method, which we call DAOE for dissipation-assisted operator evolution, using this method, what we see is that once we make gamma small enough, we find that this method follows the exact curve up to the longest times that we can capture exactly. Then it just grows linearly. It keeps growing linearly for longer times. So we can do this for a much larger system. We are not affected by finite size effects. And we see that what we would naively expect by extrapolating this data of how it should grow at longer times, our method is able to capture that quite well. So this is already very encouraging in that despite the fact that we are doing a lot of dissipation and we are far from doing the exact dynamics, we are correctly capturing the part of it that we really want to capture, which is this hydrodynamic behavior. And to make that more quantitative, one could consider the time-dependent diffusion constant, which would be just the derivative of this curve. So if the transport is diffusive, this should be linear, and its derivative should be constant at long times. So that long time limit would give you the physical diffusion constant. So the question is how well we can capture this diffusion constant with our method. And this is basically the main result. So we looked at two different models. One is this non-integrable easing chain that I mentioned before, which only has one conserved quantity, the energy. So this is something I haven't emphasized before, is that for this easing chain, there is no other conserved quantity, only the energy. So we looked at the transport of energy density. And another model we looked at is an XX ladder. So it's a 2-leg ladder with XX plus YY interactions on every bond of the ladder. And this has a conserved spin Z component, and we can look at the transport of that, which is something that people looked at before and found that it's described by a diffusion constant close to 0.95. And so what we do, first of all, we look at this time-dependent diffusion constant, and what we find is that initially it grows, but eventually it saturates to some constant. So going back to the previous question of what do I mean by thermalization time, I think one reasonable definition of a thermalization time is basically the time for this d of t to plateau, which is the time that you need to get really diffusive behavior. And what we find is that we get diffusive behavior for all sorts of dissipations, but the actual diffusion constant depends on how strong the dissipation is. So what we see here is that as we made the dissipation weaker and weaker, making this gamma smaller and smaller, the diffusion constant shifts upwards. So the question is, does it converge to something, or can we extract a physical diffusion constant out of this, which no longer depends on gamma? And the answer is yes. So what we can do is look at the estimated diffusion constant from this, so this long time value, and put it as a function of gamma. And what we find is that at small enough gamma, it becomes, to a good approximation, it becomes linear in gamma. And we expect this to be the case, that basically you could expand your diffusion constant around the limit with no dissipation, and then you would get the physical diffusion constant plus some linear contribution in gamma plus higher order terms. So what we can do is we can look at this and extrapolate it back to gamma equals 0, which would be the case with no dissipation. So this would be our best guess of what the actual physical diffusion constant is. And the nice thing is, as I was saying before, well, if you just had one of these curves for a given L star, you can do this and you get some extrapolated value, but it's hard to tell if that's really reliable or not. But the good thing about our method is that we actually have a way to cross-check this, which is that we can do the same calculation for different L stars. So modify the dissipator, increasing the cutoff of things that we keep exactly. And what we find is that for large gamma, this gives you very different results. But as you decrease gamma, they all seem to converge to the same value, to a very good approximation. So basically here we find that in this Ising model, 3 different L stars all give you 1.4 for diffusion constant up to a very good approximation. So the relative error of this is sort of around 1% or something like that. And similarly, in this XX ladder, we get the same results that, or similar result that we compare different L stars and look at diffusion constant, and at large gamma, they look very different, but by making gamma smaller and smaller, they all appear to converge to basically the same result, which is also quite close, although slightly larger than this 0.95 predicted by previous papers.
How serious do you take the result of the previous paper? Given that, I don't know what method they used, but do you think your method is better and you trust your result more?
Well, I think to be fair here, I don't think they really say it's really 0.95 and not 0.556. I think it's more that they have a plot of V as a function of some parameter, and it's around 0.95, but it's not very precise. I think within error bars they agree. I'm not sure what the error bars on this are, but I would say that within error bars they agree.
But would that mean that they also have a method that works, but maybe less general, or?
Yeah. So I mean, they just basically did ED on small systems.
Oh, I see.
But well, very very heavy ED. So they did something like more than 30 sites altogether.
Oh, wow.
Quite big.
Mm-hmm.
And in this particular model, it works quite well because this time you need to reach the plateau is fairly short. Mm-hmm. But it wouldn't necessarily work for other models where this time is longer.
Yeah.
So this model is quite useful as a benchmark because it has this sort of very short thermalization time. But for example, if you look at the Ising model, then you actually have to go to much longer times to reach the plateau. So I think in that case, they would not be able to get as precise a result with that method.
Thanks.
Yeah, so this brings me to my conclusion. So what I try to convince you of is that by doing this artificial dissipation in evolving operators, we can correctly capture the hydrodynamic behavior, sort of avoiding the limitations of many other methods, and get the correct diffusion constants, which demonstrated in various models. And again, the trick is that you have to extrapolate back to sort of zero dissipation to get the physical result. And one thing that's very nice about this method, and I think it sort of distinguishes it from some of the other things that have been proposed recently, is that you have various control parameters, and in particular, doing this for different cutoffs and comparing the results and seeing that they agree is a very good indicator that you really get the correct physical behavior. And there are a lot of possible things to explore with this, some of which we started exploring. One would be transport in disordered systems. So there are all sorts of interesting proposals. What should happen if you introduce disorder? And as you approach the MBL transition, you should get some subdiffusive behavior and so on. But these are, of course, hard to studied. There are various numerical studies, but I think we can shed some more light on it by using our method. Another case is systems which are integrable or near integrable, or things that have sort of a higher non-abelian symmetry. These are things that people have been looking at recently, and there are all sorts of interesting transport behavior that can arise here. And also just in itself, it's interesting to see whether we can capture transport in an integrable model. And we have some results which suggest that although it doesn't work as well as in non-integrable ones, but it still works quite well and probably better than many other methods or in many of the other methods that people have tried. And we would also want to extend it to finite temperatures, and well, optimistically, at some point also just compare to experiments to, we hope that we can actually turn this method also into something that you can also use to start to compare to concrete experimental results in various, for example, magnets. So yeah, and let me thank Kurt and Frank that we worked together with this, and also thank you for your attention.
Yeah, thank you very much. It was a very clear, very interesting talk. So I'll stop the recording now, and then people can just ask questions if they like.